Kelly, I'm going to pass on to you now for examples, sort of tangible, real-world examples, based on what Oluse was saying on projects implemented by IFC.
Okay, thank you very much. I think y'all are going to pull up the presentation from your end.
I'm on it. 1 second.
Thanks, Alfredo. So hello, everyone. Good afternoon. Good morning. My name is Kelly Johnson. I'm IFC's global sector lead for our investments in chemicals and fertilizers. I'm going to spend the next few minutes really a little bit more at a higher level, talking about exactly who is IFC. We're not exactly a household name. A high-level overview of some of our recent projects. And then I'll end quickly just on some of the things we look at when we are looking at projects in chemicals and fertilizers. Next slide, please. Thank you. So IFC. IFC, we are the International Finance Corporation. We're a member of the World Bank Group. And I would put a ring around that last word, group. It's not really the World Bank, it's the World Bank Group. If you look on the left-hand side of the slide, you'll see 5 different acronyms there. We love acronyms at the WBG. I won't spend time going through what each of those are, but suffice to say, our colleagues in other parts of the World Bank Group deal more and intervene with governments, with sovereign states, both from a financing perspective as well as advisory programs in tax reform, education reform, such as that. We at IFC were a little different in that whereas other parts of the bank are dealing with governments, we deal with the private sector. So we provide, we are a bank. We are self-funded. We raise our own financing on the markets. And we provide long-term loans to companies in the private sector investing in the emerging markets. We also can provide equity off of our own balance sheet. And then we have a very strong network of other financiers of all types, from leading global banks to insurance companies, to private equity funds where we can mobilize capital from those sources as well. Just a few numbers there on the right side. We were founded in the mid-50s. After the formation of IBRD, which was set up to finance the reconstruction of Europe after World War II, and has since developed into other institutions such as ourselves. We are not owned by any one government. We are owned by 186 countries globally. Probably everyone on this call, you're a shareholder of IFC. Congratulations. I hope you think we're doing a good job for your investments. We are a AAA rated institution. Thank you, Mexico. I just saw that shout out. We will do probably over 70 billion in commitments and financing this year, which should probably will be another record for us. We have about 5,000 staff around the world, most of which are based in our offices, 100 country offices, almost all in emerging markets. And we're a AAA rated institution, which allows us to take a lot of risk mitigation. Next slide, please. And quickly now, next slide, please. I'll go into some of our project examples. We have a strong pipeline of projects in biofuels, specifically sustainable aviation fuel and renewable diesel. This is a project we are working on, Acelen in Brazil. This will be about 800,000 tons a year of biofuels upon completion. If it were producing today, it would certainly be in the top 3 production facilities worldwide in this space. We are providing financing to this banner project, both on our own balance sheet as well as mobilizing financing from other developmental institutions and private sector. The facility will use primarily a mix of used cooking oil along the HEFA pathway. And then we are also working with Acelen to develop new feedstock sources that will use degraded land and not have any elements of food competition. And you'll note in each of these slides, there's a link there at the bottom, which is available on our website and other sources, which will give you a little bit more detail. Next slide, please. This is OCP is the largest producer of phosphate-based fertilizers globally in Morocco. OCP is a longtime repeat IFC client of ours. The company is investing heavily through their green investment program, a $13 billion program to reach 100% renewable electricity by 2027 and carbon neutrality by 2040. We have provided several loans to support renewable energy to help reduce GHG emissions in their operations through large-scale captive solar power. With through these two projects to date, about 600 megawatts of capacity, and we have many others in our pipeline with OCP as we venture with partner with them and provide financing in their decarbonization journey. Next slide, please. Another fertilizer project. We just committed this, the equity component, actually just week. This is a banner project of ours. This is IFC's first investment in green fertilizers, utilizing extensive hydroelectric availability in Paraguay, which upon completion, this will be 260,000 tons of green fertilizer, specifically calcium ammonium nitrate, which will supply the local region. South America is a very large importer of fertilizers. So extensive positive developmental impact here. Again, we provided a financing package here of our own, and we're also investing equity. So we will be a shareholder in this project as well. Next slide, please. Another fertilizer project, Indorama, is one of the world's largest fertilizer producers. They're one of the largest urea producers in Western Africa, specifically in Nigeria. Last year, we provided a financing to expand Indorama's urea production to just over 4 million tons per annum. We arranged a 1.25 billion financing package, our largest in West Africa. And I mentioned I included this one because in the first examples in green fertilizers and biofuels, these are utilizing new technologies, new approaches. Several of which we've talked about before, which we need to do on our path to decarbonization. But I wanted to include this one to say, it doesn't always have to be, what's just coming off the press, if you would, in new technologies. This particular project, it is using a natural gas. It's a gray fertilizer project, but it still has extensive GHG reduction components. It is using best available technology. It is using it will have high efficiencies in reduced amount of natural gas per ton of urea, as well as in water savings. It's got components of waste heat recovery, and frankly, because of its size. And it will be a consistent user an off-taker of the natural gas, it will also have a contribution through avoidance of flare gas. So obviously, when we're looking at ways to decarbonize sustainable industrialization, there's a lot of tools in our toolkit, both old, if you would, old in that current technology, as well as those we're investing in for tomorrow. So next slide, please. And then finally, I'll be a little flippant here, excuse me, but just my style. But these are some important elements of what we look for in what we think and hope. But when we move forward with a project that we think it's going to be successful, first and foremost, where does a project sit on global cost curves? Our approach is that we try and support projects and companies that are trying to position themselves in the lowest quartile or as close as possible on cost curve, because what we want to do, we want to encourage competition and induce those who are at the higher end of the cost curve to essentially clean up their game, right? To invest, to modernize, to try and bring down their cost and reduce their environmental footprint at the same time. So essentially encourage them through competition to move themselves lower on cost curves. Secondly, sponsor experience. There's an old joke. What are the three things you look for in real estate? And the answer is location, location, location. What do we look for in our sponsor? It's experience in the sector. So when we have a project put in front of us, who's behind it? Is it a global leader who has extensive experience in the sector, who's been doing it a long time, that wants to upgrade or potentially move into some of the new approaches? Or as I like to say, is it just two guys out for a walk with their dog and they come up with an idea, right? Whether it's Yara or whether it's two guys and a dog, so to speak. Feedstock. Obviously, when we look at a project, we look at the feedstock because number one, okay, feedstock availability. Is it there? Okay, great. If it's available, that's great. Okay, well, how reliable is it? If we've got a project set up right next door to wherever our feedstock is coming from and it's available, but the particular refinery or petrochemical complex or wherever it's coming from is running at 60% capacity utilization, or it's up and down all the time because of power interruptions, etc. Well, that's not necessarily helping the availability. So it's got to be reliable as well. And where is the feedstock coming from? Are you depending on a pipeline, that's 1,000 miles away? Pipeline costs add up very quickly. Or is it fortunately, right next door? And then also off-taker. We look for long-term feedstock supply contracts in our projects. On the off-taker side, that is certainly nice to have, but we don't necessarily, require an off-taker contract where you've done so for 10 years or something, because you need flexibility there. You can either protect your volumes and have some kind of take or pay arrangement, which is going to give you that reliable offtake. It's hopefully going to keep your capacity utilization up, which you need in chemical and fertilizer projects. If you get below 80-85%, you're probably going to start having some issues. But obviously, that's not giving you any price protection, which, as we all know, in this business, volatility can happen at the drop of a dime. So do you want price protection? So you've got a floor there, if prices or margins drop. But if you do that, you're not going to get the volume protection. You can have one, but you're probably not going to get both. So that's something obviously we take into consideration. And last but not least, of course, is what kind of technology are we looking at? We can support technologies that have been around, for forever and a day. but we also are, provide our financing in projects that are taking very, very novel approaches. I didn't include it in the slides. Perhaps I should have, but for example, we're looking at a very large greenfield methanol facility in Latin America that will be ultra low carbon production, which in my mind, it's actually several projects put together. It is involving green hydrogen. It's involving carbon capture. It's involving electrification of the SMR at a scale that has not been done before, each of which has its own risk. But we are supporting that as one of our banner projects. That is it from my side. Thank you for your time and attention, and happy to take any questions. Thank you, Alfredo, for sharing the slides.
Thank you, Kelly. We'll wait for one more presentation before we go into Q&A. But thank you for the coverage of projects. And if colleagues want to hear more about the projects, I know that IFC publishes some data publicly or summaries on projects, or they can reach out to Kelly directly. We'll provide those emails as needed. Boris, I'm going to hand over to you right now.
Yeah. Okay. Can you share my presentation?
Thank you.
Okay. Super. Okay. Hello to everyone. My name is Boris Nekrasov, based in Istanbul. I'm an energy specialist. I've been with IFC Global Manufacturing Team several years, serving as a focal point for climate assessment of manufacturing projects. So in my short presentation, I would like to share our experience in GHG assessment of chemicals projects, to share our experience in specifics of the projects, to present some practical cases, and to share lessons learned and some tips. Next slide, please. Okay, first of all, I will start from baseline and project emission assessment, so as well as emission reduction calculation. As already previously discussed, project emissions, also known as gross emissions, refer to GHG emissions expected to result from all project activities. It's needed to identify all GHG emission sources that will change as a result of the project implementation. There are three scopes of emissions. First of all, scope 1, direct emissions from operation activity on the site. Scope 2, indirect emissions from generation of purchased electricity or heat or cooling. And finally, scope 3, indirect emissions associated with supply chain, both upstream and downstream. Baseline emissions or counterfactual scenario represent emissions that would occur in absence of the project. Baseline must account for all emission sources included in the project scenario, plus any additional sources that change as a result of the project implementation. GHG reduction calculated by subtracting the project emissions from the baseline scenario emissions. The same approach is applied for the net emissions, but with the sign minus. Net emissions are calculated as project emissions minus baseline emissions. So in all cases, we use ex-ante approach to calculate GHG reduction, to calculate expected gross emissions from the project, and to calculate GHG emissions from the counterfactual scenario. I would highlight some specifics of the project emissions assessment for the chemicals projects. Typical emissions categories include feedstock as upstream, that includes in scope 3, on-site chemical reaction accounted for scope 1, and product end use, typically feedstock and fuel as downstream, scope 3 emissions. Since leakage and fugitive emissions are often not directly measured on site, in most cases, the mass balance must be developed for accurately assess these emissions. So next slide, please. Collecting complete and accurate input data is one of the most challenging aspects of the GHG emission assessment. Before collecting input data, the project boundary must be defined, including production facilities, utilities, and auxiliary systems. So a description of the technological process, including key chemical reactions, is required to identify operational emission sources. In most cases, standardized data collection template could be used, but it needs to be tailored to reflect some specifics of the projects. Main inputs typically include raw materials and feedstock, all energy resources consumed in both technological process and utilities. It also includes electricity, both from grid and produced on the site. It would be useful to indicate the share renewable part on the site. Finally, fuels and water, and also purchased heat in some cases. If the project affects fleet operation, fleet fuel consumption should also be included in the assessment. And main inputs would be the following: products and sub-products. This info is needed for mass balance and for calculation of carbon intensity, if it is required. Direct GHG emissions that include emissions from technological process and other sources of emissions, for example, from waste and wastewater. Sector benchmarks and market data are essential for determining the carbon content of input materials and for comparing product carbon intensity against best-in-class sector performance. So about the source of information, unfortunately, there is no only source of information. So multiple data sources typically used to compile a complete data set. I could mention the feasibility study served as a primary data sources. In some cases, the EPC contractor's performance guarantee could provide specific energy consumption data for final and intermediate products. And finally, sector benchmarks that would be used to compare the final product's carbon intensity against best-in-class sector performance. So please, next slide. So I would share some practical cases to demonstrate how we apply this methodology. The first case is integrated plant for urea production. So the project includes urea production plant comprising 2,300 tons per day ammonia plant and 4,000 tons per day urea facility. The feedstock is natural gas. So the project is designed to partially utilize CO2 emission from ammonia plant and urea production. As for the baseline scenario, it would be compared with the ammonia purchased on the open market. Under this baseline approach, the GHG emissions from ammonia production are classified as a Scope 3 emissions. In the project scenario, the production unit is integrated into one site with urea plant. This integration enables to utilize CO2 emissions from the ammonia plant directly in the production line. Multiple data sources were used to compile a complete set. The feasibility study served as the primary data source. The EPC contractor's performance guarantee provided specific energy consumption data for final and intermediate products. Grid emission factors were applied for Scope 2 assessment, and certain benchmarks were used to determine the carbon intensity of imported ammonia and to compare the final product's carbon intensity against sector average and best-in-class performance. By integrated ammonia and urea production into a single plant, this decarbonization approach results in urea with one of the lowest carbon intensity in the world. Please, next slide. Okay. The second case is methanol production with utilization of flare gas. The project is 1.8 million ton per year methanol production plant. Natural gas is used as both feedstock and fuel for the captive power plant. And the project will utilize 100 million cubic meters of gas that is currently flared. As the baseline scenario, the current situation were considered when the natural gas-based methanol is produced. Flare gas is not utilized in methanol production in the baseline scenario. In the project scenario, flare gas is redirected to the captive power plant, replacing natural gas previously combusted in the captive power plant. This results in the net reduction of natural gas consumption. Multiple data sources were used to compile a complete data set. Feasibility study served as the primary data source, and the EPC contractor's performance guarantee provided specific energy consumption data for final and intermediate products. And finally, sector benchmarks were used to compare the final product's carbon intensity against best-in-class sector performance. By utilizing flare gas as a decarbonization measure, the project will produce methanol with a carbon intensity aligned with the best industry benchmarks. Next slide, please. Okay, next. Okay. And finally, I would share some key specifics and lessons learned for chemicals projects. Standard questionnaire don't cover all data and specifics required for chemical projects. So a tailored data collection questionnaire is needed for each project. Typically, multiple data sources must be consulted to compile complete information. Including the chemical process experts on the assessment team is critical. They can help define the project boundary accurately, develop the baseline, counterfactual scenario, and clarify questions related to the input data. Energy resources such as natural gas can serve a dual role in many projects, as feedstock for chemical process and as fuel for power and heat generation. Chemical reactions within the project boundary must be carefully assessed, as they can act as both a carbon sink and an additional source of emissions. Certain projects can export heat and electricity generated by exothermic reactions, for example, ammonia and sulfuric acid production. These energy streams affect the overall energy balance and GHG emission model accordingly. And finally, carbon intensity calculation may be necessary to demonstrate best-in-class efficiency, particularly for greenfield and expansion projects. So a reduction in carbon intensity confirms the decarbonization impact of the product, even when absolute emission increase. So I would stop here and would be happy to answer to take any questions later. Okay, thank you.
Thank you, Boris. And I'll hand directly over to Janak, who'll be moderating questions from the audience. I know Janak's connection was a bit spotty. Hi, Janak.
Hi. So I'm having connection issue here. I was intermittently disconnected. I think we have a couple of minutes for Q&A. And yeah, so I encourage you to ask questions from the experts. But in the meantime, I have a couple of questions reflections to Boris' presentation. Particularly, what is your suggestions based on your experience, right, in terms of determining the counterfactual in the given country context? So there could be whether you consider continuation of your current situation as the baseline, or you consider more forward-looking, where you take into account the country's policies, raising ambitions, and then kind of the barriers and all those, like what is the baseline you consider as credible that attract investments, right? So that is one. And second one on natural gas, right? The import of ammonia. So you said that this project, exceeds the current market benchmark. So when you factor in the emission factor of the export ammonia, so do you know the source, the source where this ammonia is produced, or it is from the market? And then how you determine the emission factor that is exported, the ammonia you have exported from the market? So it can come from anywhere. And then whether you have taken into account the upstream emissions associated with the ammonia that is produced elsewhere, the transport, and then the source of natural gas, etc. Could be more complicated, but maybe some aspects also would be useful for our clients in that.
Okay. I will start from the last question. Yes. So as the ammonia is purchased on the open market, so we could not apply some. Yes, we could apply some specific carbon intensity of the ammonia for some particular part purchased in some specific time. But based on the conservative approach, we use the best-in-class carbon intensity. So for some hypothetical case, if the ammonia purchased with the lowest carbon intensity from the open market. For the first question about the baseline scenario, so if I understood correctly your question about how to develop the baseline scenario, yes. In each case, this is some challenging task. You need to be some like inventor to develop the counterfactual scenario, to develop the baseline. It's not obvious. It's not obvious case. That's why it's recommended to attract for this task some staff from project staff, chemical experts, to consider some options and to develop the most realistic, the most feasible baseline. So it's not formalized task. That's our experience. Hopefully I answered the question.
Yeah, thanks, Boris. I think we can continue the discussion on the baseline aspect. It's quite critical. But yeah, Matthew, please proceed.
Yes, thanks very much. My question is really about standardization. So I think I was struck in the presentation from Boris on highlighting in chemicals projects these three different areas that are particularly important to consider, and that might make chemicals projects different from kind of general GHG accounting in other sectors. One of which was feedstock upstream, which was under scope 3. Another was chemicals reactions on site under scope 1. And then the product feedstock and fuel downstream, which would also be scope 3. And the reason I found this so interesting is because when we had developed GHG accounting guidance for other sectors, often there's kind of operational preference to focus only on scope 1, or maybe more limited aspects of scope 2 and scope 3 in defining assessment boundaries. And yet we see clearly, I think, based on the sector that, you can't kind of perhaps have such a clean prioritization of scope 1, then 2, then 3, et cetera, because there may be aspects within these projects in other scopes that are, particularly important to the overall GHG accounting. So that said, my question is kind of how much does IFC, for instance, standardize across chemicals projects, either, let's say, within ammonia projects, but even across different chemicals? How much kind of wiggle room is there to decide which activities or which scopes are the most important to focus on within the context of each project, versus how do you kind of find that standardization more at portfolio level? I hope that's clear.
Okay. So I will take these questions. So there is no some standard procedure for chemical project assessment. Each project needs some tailored approach depending on the availability of the data, especially for the data needed to assess scope 3 emissions. In some cases, we have some robust data to assess scope 3 emissions. In some cases, we don't have such data. Also, depending on the nature of the project, if scope 3 emissions is not included in the project, scope 3 emissions is not affected to the projects, and if there is no available data, so we skip this assessment. But in some cases, like the ammonia example, when you replace the imported ammonia with the ammonia produced on the site, yes, in such case we need to assess somehow scope 3 emissions from the purchased ammonia. So it's again, in conclusion, so there is no standardized approach, but so we need to be realistic, and we need to try to assess if we need this data.
Yeah, thanks, Boris. I think in terms of standardization, I think the approach is standardized, right? You have a standardized methodology, kind of the concept, like how you estimate your emission reductions, taking the amount of emission sources, etc., etc. But when you get into the nitty-gritties, right, in terms of using the your actual data, how reliability is versus the more conservative estimates, I think that may vary. But the approach, kind of how there is like a kind of the guidance or set at the international level at the GHG protocol or in the carbon market standards, like how you credibly set the baseline, what are the kind of different aspects you need to consider. But then when you get into the project, maybe, yeah, so depending on the country context, project context, you have some flexibility how you can boils down to the estimation. So I think this is an excellent discussion, and then we would like to hear more from James, like how all these aspects has been built into the country specific model. I think he's bringing he's sharing the experience from Mexico and Uganda. So maybe we can continue again the discussions based on his presentation. Madhu, anything you want to add?
No, Janet, that sounds great. Yeah, a quick introduction. CISEPUEDE works at the country level. So we're looking sort of at an aggregation of these sort of tools up at the national level, but also cross-sectorally, and taking account of also economic and socioeconomic factors. Thank you, Janak. James, handing over to you.
Great, thank you. Nice to meet everybody. My name is, first off, everyone can hear me, right? I'm on headphones, so I want to make sure. Okay. My name is James Syme. I'm an associate professor at Tecnológico de Monterrey, and have had the pleasure to work with the World Bank on a number of projects using our modeling system called CISEPUEDE. Are there some? I see they're coming up. Great. Cool. Okay, so I'm going to just bring it out to a 1,000-foot view now. We've been talking about individual projects. I'll talk about a little bit about how we've dealt with this at the country level throughout a number of projects. So if we can go to the first slide. I'll give a little bit of a background on what this modeling system is. So it does stand for something, stands for simulation of sectoral pathways and uncertainty exploration for decarbonization. The original motivation for this work was a project in 2020 to assess the costs and benefits of decarbonization in Costa Rica. Following on with this work, I grew from Costa Rica and Chile into a much larger project focused on Latin America writ large. So we did 18 countries writ large, and we needed a modeling system that could not only approach things from a cross-sectoral perspective, but that could be used to develop robust strategies, i.e. testing uncertainties, and looking at a wide range of strategies for a country to meet decarbonization or decarbonization goals, and then think about the costs and benefits associated with those different strategies. So when can we go to the next slide? So what is Si Se Puede? We call it an integrated modeling framework. It's not an integrated assessment model. It shares some characteristics with it. But the idea of it is it's a bottom-up integrated simulation model. It's written in Python and Julia. When I say bottom-up, it's based on the IPCC guidelines for national greenhouse gas inventories and accounting. It includes a number of different optimization models across energy, AFOU, IPPU, and circular economy. Includes some biophysical models, but it doesn't include biophysical feedbacks, which you get in integrated assessment models. So, if you decarbonize the country or region that you're looking at, it doesn't affect the energy system or the global energy balance of the globe, the world as a whole. So one of the things that we have in this model, when I say default regional specification, it's region independent. So you can, we've worked on this. I'll talk a little bit about some of the projects, but it can be done at the country level, at the state level, at the metropolitan level. Just matters the kind of data that you're actually feeding it. We do have a preliminary global database with 170 some countries. Now I say preliminary because it's a starting point for most cases that we work with, and then usually when you use it and you apply it to a specific country context, there's a data collection effort that's undertaken, a validation effort to make sure that it lines up. So right now we have a decent starting point for most countries, and this can always be improved upon when you're able to actually work closely with partners in the region to access, maybe government-specific data that we can't find otherwise. And then one of the other pieces that this does also include, and was one of the key motivating factors, is a really robust experimental management system. So myself and my colleague, Edmundo Molina Perez, who was unable to join today, we specialize in a field called decision-making under deep uncertainty. So a lot of this is, when we think about climate change planning, we're thinking about making plans and identifying strategies for decarbonization 30, 40 years in the future. And it's an uncertain problem. So this modeling system includes a robust framework for testing and stress testing those uncertainties, and then comparing different strategies or portfolios of policy transformations against a range of different futures to help you identify robust pathways. Let's go to the next slide. Okay, so as I said, integrated assessment framework. This is what the model looks like. Okay, this isn't what the model looks like, but this is a graph trying to convey what the model looks like. So it's specified in 5 separate sectors. There's a socioeconomic, IPPU, or industrial process and product use, circular economy, AFOU, and then energy. When we say socioeconomic, it's a very, very simple model. This is not a general equilibrium model. It takes GDP and population as exogenous, and then everything kind of flows downstream from there. So in the IPPU sector, we have industrial production, and this is where we have so this is one of the places where we deal with chemical production. Now, as we're talking, distinguishing between scope 1 and scope 3 emissions, because this is an integrated model, it includes a lot of those, at least for what is endogenous to the region that you're looking at. So I'll speak a little bit more about that. But just to kind of follow, and we can think about how emissions are kind of traced through here. So in the IPPU sector, that's where we deal with estimates for industrial production. Usually in the model, you start with there's two ways to run this. So you can start with some kind of production level and then specify elasticities to GDP. And in an industry, it'll just adjust as GDP goes forward. And that would be for demand, not necessarily production. And then you can also just specify a pathway forward. Within those, once you have a production kind of set, then you have IPPU emissions associated with it. So those would be, I think, the direct scope 1 emissions you're thinking about. In going back to the cement example, like calcification emissions from limestone and clinker production. Then we have the energy model. So those demands get sent to the energy model, and the energy model, this is an accounting separation. So we treat with then what are the energy requirements to produce that much. And of course, you have imports and exports affecting not only the fuels that are being used, but the actual production in IPPU. Another kind of link that I want to highlight here is between IPPU and AFLU and energy. I'll start there. So within there, one of the key trade-offs that we see, and I'll talk a little bit more about, but is between, say, organic substitutes for synthetic fertilizers. So we have kind of traced in here things like livestock manure management. It can potentially be used as something to reduce the need for synthetic fertilizer production. We also have the connection with circular economy, which is where we include wastewater treatment. So within there, you can also pull, say, sludge from wastewater treatment facilities and potentially use that to mitigate the need for synthetic fertilizers. So when you do that, that affects the demand for fertilizer production and synthetic fertilizer use. So a little bit more about what we have as far as gases. So the model is designed to estimate masses of gases between the kind of big three, right? We've got methane, CO2, and N2O, but then we have a whole bunch of PFCs, HFCs, SO6. These are largely coming from, so these are by industry. I'll talk a little bit more about where they come from. But then what this is used for primarily is to assess policy transformations. And so I'll talk a little bit about the transformations. But when I say a transformation, what I mean is an outcome. So this model is not used to assess things like, what's the impact of a tax, right? How does that change things? What is exactly the impact of a ban? It's used to assess and find emissions targets within a sector, assess the kind of costs and the high level costs and benefits of getting there, and then kind of strategically outline how the system might arrive at the targets that you want to hit. So let's go to the next slide. So just a couple things on considerations for this. So data collection can be onerous. This is especially if you're going to complete an entire integrated assessment. There's a lot of variables that go into this model. One thing that can mitigate that a little bit is it can be broken out and run sector by sector, so you don't have to run all the sectors individually. There are a couple, maybe things you might want to have in there. We have biomass connections now between AFLU and energy and IPPU. So if you have harvested wood products, that can actually affect the biomass pool, and then that affects land use, and both of those will affect the availability for energy. Things like biomass gasification or electricity from biomass production. So depending on what kind of assessment and how far you want to go, you can narrow down the data collection requirements to just be, say, I care about the IPPU scope 1 emissions from chemical and ammonia production to I want to look at what's the kind of impact on the system as a whole. The other thing is this is only available in code right now, so we are working on a kind of a shiny GUI, but it is we have a wide set of tutorials and things on GitHub, and we're working on a chatbot and et cetera, but it's all code based right now. Let's go to the next. So just a little bit about where this has been applied. So we've done a lot of work partnering with the World Bank to support country climate and development reports. Of course, the original motivation for this was in 18 countries in Latin America. So the report, which was an IDB report, is a Latin America, costs and benefits of decarbonization in Latin America, but that was done by running for 18 countries and then combining those into a composite for the region. And of course, there's a list here of countries that we've been working on right now. There's a lot of work going on as we wrap up a NDC3 support in Uganda and some work in Mexico that's been ongoing. I did this in Louisiana to help support their climate action plan that should hopefully be released shortly. Doing work in Mexico City on the state of Oaxaca. And then, of course, we're using this to look at the impacts of urbanization in metropolitan areas in Mexico. So let's look at the next slide. Okay, so this is just looking at a very high level kind of output from the model. So oftentimes when we run this, we're running across sector, we're looking at the impacts of different strategies and how those affect emissions. So a little bit about the baseline setting. This is a difficult exercise. Usually this is something that's undertaken with in partnership with stakeholders. You can specify a whole bunch of different baselines. One of the advantages of this modeling system is you can specify a baseline and then you can stress test strategies against a bunch of different baselines. So if you have an assumption about how GDP evolves over the next 30 years, we can stress test that and let's say, what if it grows more? What if it grows less? What happens if the elasticities change over time? What happens if population changes? What does that do to GDP per capita and then impacts on transportation, demand for food, demand for land, et cetera, et cetera. And then, of course, demand for land and crops and production will affect fertilizer demand, which then is, can affect how, industrial production and the emissions that we're thinking about. So this is just showing, a picture from the original report on Latin America, but you can see there's a baseline, which we called traditional development. And then, of course, we've got 4 different strategic pathways that were evaluated, one called incremental improvements, a supply side of solutions, a consumption changing, and then let's throw the book at everything and see what happens. Let's go to the next slide. Okay, so the model, while it can be used to answer these aggregate questions, it's important to note that every region is treated differently. Every region has its own economic characteristics, its own input demands, export, import profiles that affect how the emissions are accounted for in the system. So when we think about comparing 2 countries like Uganda and Mexico, Mexico right now is focused on developing ammonia production in the long term, to have kind of ensure independence in the global economy. They already have a robust petrochemical industry in Mexico. So it is important to make sure that we're considering a wide range of transformation and abatement options for Mexico to ensure kind of these targets are hit in the long term. Now, a country like Uganda that doesn't really have much chemical production right now and hasn't targeted that industry for growth in the future. I mean, they've targeted a number of other areas like mining, building out cement production, clinker production, et cetera, et cetera, et cetera. So they're looking to develop other industries, maybe not as much on the chemical side. There's less of a concern in the long-term strategies to think about how do I abate ammonia production, right? How do I develop this? Now, that's not to say it's ignored. Green hydrogen is certainly a part of, plans that have been considered. There are projects that they're considering around that. But when we look at kind of the different strategies that we take, increasing M production in Uganda is probably going to be really, really, even if you did it without certain abatement measures on the industrial side, the impact on land use and deforestation would be so large that would outweigh kind of the whole system picture of emissions from at least in the medium term, right? From, say, implementing and making sure that ammonia is carbon free, or that they have green hydrogen production in-house. So there's an interesting kind of, and these can be these transformations can be assessed over the short term, the medium term, the long term. The timing is important depending on the country you're in. In Uganda, it's very important to make sure that development priorities are put first, right, and that the economy can grow. So we think about a much longer term strategy rather than when we've been working with Mexico, which is a little bit more immediate when we think about the NDC and those kinds of things. Next slide. So one of the other pieces that we include here are just high level cost and benefits across the economy. So things like capital investments required on the energy infrastructure side. Of course, if you're increasing the production of certain goods, then energy demands are going to go up. So we have estimates on the capital cost side. We have estimates of co-benefits, including things, productivity increases in production, health benefits, air benefits. We've added some since this graph was made. So we have indoor health quality, ecosystem services for a number of different categories of land, et cetera, et cetera. Okay, next slide. I want to make sure I don't, I need to get through some of these. Okay, so I will just, IPPU, this is going to be more, I think, the scope one. Again, we account for processes and product use, but we also account for the energy side of things. And the energy side of things would be, can include a number of feedstocks. I will note that for ammonia, I'll get into this a little bit with ammonia production specifically. It's part of our energy bond model. Other chemicals can be kind of specified. The model's very, very versatile, so you could add new industries to this if you wanted to. You can specify specific emissions factors that are, appropriate for the country or region that you're analyzing. Right now, what we have is based on a bottom-up DB database for that's global in scope from ESSD, and I have the. Yeah. Let's look at the next slide. So some of the transformations that we include, of course, include increasing efficiencies. We do have recycled products and changing kind of the feedstock stream. Reducing F gases. So those can be any of the 32 that we've got in there, HFCs, PFCs, other fluorinated compounds, SF6. N2O is included in there. And of course, we have offsets in AFOU and circular economy that can affect fertilizer and chemical production, as well as on the energy side, things like biogas, et cetera. Next slide. Okay, so a little bit, about what we can do as far as kind of on the country level, thinking about ammonia. So we included in our fuel model because ammonia is turning into a real prospect for overseas shipping and kind of as an energy carrier. So we wanted to make sure we had it included in there. So because it's in there, we do have different feedstocks available for the way, and I have a map of it. But the way that, actually, can we go to the next slide first, and then I'll just come back to this and finish. So, we've added a few things to this since this diagram was made. But the fuel processing and refinement model, the way we treat ammonia production is hydrogen as a feedstock. And then we have, different methods for producing hydrogen depending on kind kind of average shares by industry. So that can come from SMR, it can come from gasification, where one of the updates we're finishing is that explicit link between the land use and biomass availability and things like biomass gasification, which is a potential additional source for besides electrolysis for clean hydrogen. We have reformation in there. And of course, this is all built into the larger energy system as a whole. And then if we can go back up to the previous slide. Thank you. So of course, we have then the ability to model the different types here. We've got electrolysis or biomass gasification. We've got standard ammonia from natural gas SMR. These are high-level ways of doing it. So we're not modeling, individual plants. It's kind of aggregate at the region level. But then we can, within the kind of scope of the broader system, assess certain trade-offs. So if you move to electrolysis, what's the impact on natural gas imports and production, which can affect fugitive emissions. It can also affect it affects your energy profile. So what does that do depending on how you're actually meeting those energy demands? Is it coming from renewable sources? Is it not? And then, as I spoke about with the biomass side of things, how is that affecting the availability for other things? In Uganda, biomass extraction is a massive part of the system. So you have to be able to move to sustainable biomass, things like crop residues, et cetera, to make sure this works. But then that can affect feed availability and your ability to do conservation agriculture. So there's kind of a lot of pieces that can sit in here. And of course, when we think about the impact on nitrogen demand for fertilizer, how does using organic amendments change that system demand for the country over time? And the final piece I'll add here is, even though the model does not include a economic module per se, it's not a general equilibrium model. We have combined this with input-output models to kind of assess, what's the impact on the demand for jobs in the country? What's the economic impact of these different actions, right? So we're working on a number of different integrations with Mindset and CPAT and things to kind of help expand the scope beyond just the technical costs and co-benefits that we do now to think about broader economic impacts. Okay, I'll stop there. It's a little bit longer than I expected.
Thank you, James. No, and this is highly relevant because I think what this model is doing is looking actually at cross-sectoral approaches, which is relevant to our countries that work not only on industrial decarbonization, but have other programming in place as well, and also for their public audience to understand what implications in this sector means for the national strategy as a whole. As Claudio mentioned before, the SIF does take a national systemic approach, while the programs are split between different countries. A program-specific industry decarbonization for Türkiye, industry decarbonization for country X or Y. Those countries sometimes have other SIF programming, but also certainly other climate programming. And this sort of approach allows countries also to bridge those differences. I'll hand to Janak for questions and to colleagues on the call, especially colleagues who are working on investment plans or defining indicators, baselines, etc. Please come in, and we can also have follow-up calls with the colleagues online.
Yeah, hi. I think we have only a couple of minutes left, right? So maybe I think this is an excellent session, and if we can ask one or two speakers just to, for the benefits of the participants. So we have heard like the high level kind of the modeling, right, at the national level, right? And then some models which can, which goes pretty much depth into the project level, right? So, but in the context of, CIF investment plans that demand sector baselines and mitigation scenarios, so how we reconcile? So for country A, right, which they do not have like the national level, modeling, whether that is the kind of the first step that they have to build the modeling to inform their strategies for mitigation investment plans that inform the project pipelines. Then you align your whatever, like the baseline scenarios, mitigation scenarios, and you target accordingly. Or it can go without having the high level modeling, and you deep dive into the sectoral level. So I think that still there is a disconnect, but maybe speakers can help. What is the methodological process you suggest for ensuring this coherence between the two level of analysis? I think that would be helpful.
Yeah, no, I think that's a really good question, because it's a modeling exercise, right? And so it's never exactly perfect. One of the ways that we've really, so for example, when we work on maybe supporting NDC actions, NDCs can vary in their specificity of the projects. They may be kind of high level, like we want to do this kind of thing. We want to make sure we electrify rail and increase it by a number of percent, right? So what we do is we try to take stock when thinking about the plans that are in place. So there's two things. There's setting a baseline, which can include thinking about plans that maybe are in place or have already been paid for, et cetera. Making sure that when we model things, it reflects those projects kind of in aggregate. So if you're looking at, maybe there's already energy systems in place, and maybe there's a number of large industrial, like for example, in Louisiana, there was a large liquid net LNG export facility that's supposed to come online, I believe, in 2027. And it was really, really important that our baseline reflects that. So we made sure that we have this capacity built into the energy model. We made sure that we have exports reflecting that. And then you think about, okay, let's go through the options, the mitigation options that are there. And some of those might be really, really project specific, and some of them might be really, really vague. So when they're project specific, we do absolutely our best to make sure that our modeling reflects kind of the estimated impacts of those projects, whether it be an emissions impact, an energy impact, a cost impact associated with it. We make sure that our high level aggregate modeling reflects that. And then when there are things that are maybe a little bit more vague, we try to capture what's in there. And then of course, this goes through a review process with whoever the stakeholders are who actually think about this. And then when you have people who are very, very knowledgeable about the projects, it's very, it's more helpful, because they can help kind of say, yeah, this sounds right, or this is absolutely wrong, fix this, make sure this aligns in a way. So it is like this, you're trying to take something really high resolution and then bring it into the 1,000-foot picture. Did that help? I mean, I hope that helped answer that.
Yeah, thanks, James. Anyone who wants to add or any questions? Otherwise, I hand over to Mudu.
Thank you, Janak. And colleagues, I might hand over to Alfredo, who's been the lead on organizing these clinics and this academy, to close with closing remarks. I know we're over time already. Thank you, Alfredo.
Thanks, everyone. Can you hear me?
We can.
Wonderful. Okay, so first of all, I would like to thank our speakers. I mean, fascinating speakers. For the past 3 hours, we've been able to hear about overall methodologies, about international standards. We've been able to hear about specific softwares and programs that we have that are out there for our different industrial decarbonization country teams and MDBs to use, from Sustain 360 to Si Se Puede to obviously different models that our MDB partners use as well, like the IFC. And I think it's been fascinating to hear the vast international experience and the different case studies that could be used for the specific overall for industrial decarbonization, but also when we dove deeper into the chemical section. So with that in mind, first of all, kindly big round of applause and thank you to all of our of our speakers. I'm really, again, thankful from the Safe Secretary behalf. And before everyone leaves, just a quick reminder first that we have a second session next Tuesday at the same time. So it will be 8 to 11 a.m. DC time again. And this session will dive deeper into two specific subsectors within the construction materials one. So we'll see into different GHG methodologies and MDB projects in decarbonizing both cement and steel as part of the conversation. And we will have, again, MDB partners all the way from ADB, World Bank, IFC, and others presenting case studies and international experts as well on the GHG methodologies. So we're definitely looking forward to seeing everyone in that specific session. And for those Group B countries from the Industrial Decarbonization program, also a quick reminder that this Thursday, May 7th, you have the kickoff or orientation call for the Bridge Initiative that the Safe Secretariat is leading. So hopefully we will be seeing you in a couple of days again. With that in mind, thank you, Madhu, and thank you, obviously, everyone and here in this call for attending and for speaking. Looking forward to next session.